what's the processes going on inside a star that makes a star a star. How does our star compare to other stars? And then what happens at the end of the story? What happens at the end of a star's life? Introducing the sun, sort of. And that's, some people might think of that as a boring astronomy target, right? The sun, but the sun actually is extraordinarily interesting, and it's a lot bigger than you think it is. That's the sort of, and we'll get into that sort of in a moment. A baseline understanding. So first of all, let's address the first question, which some people have. We do get asked this. Yes, the sun is a star, and if you were in the another solar system somewhere in the universe, you might consider that star to be your sun. So they are interchangeable as far as astronomy goes. However, when compared with data and measurements of other stars, the sun is really kind of an average star, kind of unremarkable. However, we have to recognize as that things are complex as human beings, not just as amateur astronomers or scientists. We also have to acknowledge that the sun is emotionally, historically, geologically, evolutionarily, and physically indispensable to us as a species, the collective human race. We wouldn't be here without it. And so to us, the sun is the most important star in the universe. And that's very rare. That duality is very real. All right, so I said I'd explain sort of. What does that mean? Astronomers are actually actuaries, and I said that successfully, and I will not do it again. The sun has been around for 4.6 billion years. Humans have been around for about 200,000. And there are some ancient Chinese astronomers and records that we have. Astronomy going back thousands of years, a lot less than even 200,000 years. And so the sun has been around for a long, long time. We've been around for about 0.004% of that time. So how long have we actually observed the sun? Very, very little, right? So when looking at stars, astronomers not only have to take into account the speed of light and the expansion of the universe, but also their statistical variation. And for us, that isn't a problem, that's a feature. Why? Because the sun has logistical advantages to us observing it. As I said, ancient astronomers have been able to observe it for thousands of years. It's very close, easy to observe, or there's challenges to observing it too, and I'm not saying that it's easy, but easier than other stars to observe. And our particular star that I'm going to talk about tonight is a sun-like model. In other words, we're taking knowledge from our close neighbor and very important star, but we're also applying all the knowledge we get from all the other stars we can see in the Milky Way and around us, and we're combining that into a comprehensive model of what a star is. And that's the star we're talking about. So it's going to look a lot like the sun, but at the same time, it's every star. Hey, buddy, I told there would be pictures, right? We don't want to just see text on the screen there, so let's start someplace. We're going to start at the Solar and Heliospheric Observatory, SOHO. There's the website right there. The picture I'm going to show you is current as of August, early August of this year. HMI, that's the title that you want to see to get this same picture, but today's version, because it's updated regularly. It's what you can see with a standard solar filter. They call it a white filter sometimes, or a beta filter. And it's a little oblong because of the shape of the screen there, but that is our sun in early August. And you can see, of course, two features right there. Sunspot, and there's a little bit of a something going on there, not quite as visible as a sunspot. Why am I not showing you today's? Every time I look at this presentation, I am tempted to update it with today's, because I want you guys to go to that website and take a look at today's sun. All right, and I have some information here. Today, they're at 1024. Actually, sunspot 2776 is on the sun. You can see 2770 and 2769 up there. Sunspot 2776 is there. So search in your, if you don't remember that website, search NASA and SOHO. You need the NASA, otherwise you get a lot of pictures of stuff in the city. So take a look at NASA and SOHO as your keyword search, and that's one of the first things that'll come up on your in like Google. All right, the inside scoop. Let's talk a little bit about the materials of construction of a star. In astronomy, metals are elements that are neither hydrogen or helium. The Big Bang created mostly hydrogen and then a little bit of helium. They are by far the most abundant elements in the universe. So you can see here an approximation of the various quantities of stuff in the universe. Hydrogen at 71 and change percent. Helium at 27 and a little bit more percent. And then metals as the balance, about just under 1.5%. Metals really isn't satisfying, though, is it? Because that's everything else. So what is everything else? Well, let's zoom in here a little bit on this spectra. These are absorption lines, and let's talk a little bit about what an absorption line is. So if you have a source of light, and you put something, a substance, in front of it, that substance, based on electrons moving up and down in orbitals around the molecule, around the element, will absorb frequencies of light. And when they absorb the frequencies of light, and they say come back out, the energy from that absorbed light comes back out again, that light doesn't necessarily travel in the same direction that you are. So the sun, something in front of it, and then you. But that something in front of it might spit the light back out in a different direction. That results in these absorption lines. And you can tell what that substance is because different substances absorb different frequencies of light. Does that make sense? So that's how we can tell kind of what's going on the photosphere of a sun, is that we get these absorption lines and we can analyze that light to tell what's going on in there. Whoops. Here's abundances on the surface of various suns on this other side here. This is logarithmic, this scale here. So you can see hydrogen and helium way up there. That's all the stuff, the Big Bang stuff. Then something's going on here because these guys are really low, these next three elements. And then these guys all the way down, sort of, it seems like a pattern's happening here. That stuff's actually made in various stars. This might tell you here, because these guys are different, that they are not made in stars. And these guys here, since they are also different and much higher, they were made in a different process. We already said that they were made in the Big Bang. All right, let's play a game. Some more things about trying to get our minds around what a star is. Try to compare these values to something you know here on Earth. core temperature is 1.56 times 10 to the 7th degrees Kelvin. Now, Kelvin is an absolute temperature scale. 0 would be about 273 Celsius, which is 32 degrees Fahrenheit, would be about 273 degrees Kelvin. All right, so that's a comparator here on Earth. So it's really hot. Core pressure is 1.97 times 10 to the 11th atmospheres. How many atmospheres is it here on Earth? 1, right. So again, massive pressure. The mass is 1.9888884 times 10 to the 30th kilograms. Kilograms we're kind of familiar with, right? Diameter, kilometers, 1,391,400. Distance, 1.496 times 10 to the 8th kilometers. That's about 93 million miles. That distance is also 1 AU, and it's also 0.000016 light years. Let's just talk about the power of knowing those numbers, which are huge. Let's talk about a little bit about the power of the sun. The last one is 3.828 times 10 to the 26th watts. Let's talk a little bit. Anyone here camping tonight? I asked the question earlier, no one was camping. Anyone here? No. All right, but we know campfires, and we know that we can say sit 10 to 15 feet away from the campfire on a night like this and still feel the warmth from the campfire, right? But we back up another 5 to 10 feet and we can't feel the campfire anymore, correct? So like 25 feet away, can't feel the campfire anymore. The sun is 93 million miles away, and you can close your eyes and put your face there and feel it on your face. That's how powerful the sun is. So what is in the sun? Combining some of that information together, what is in the sun really? It's an incredibly hot, incredibly massive, and it's also under gargantuan pressures. It is not made up of matter as under those pressures and temperatures, etc. We don't experience that here on Earth. We don't have anything that we can just think of ourselves without doing research in a lab on something that we can just come up with regular experience here on Earth. It's a fourth state of matter. That matter is called plasma. And what is plasma? It's mostly made up of hydrogen nuclei, protons, helium nuclei, which are also called alpha particles, and free electrons. So it's a soup of all that stuff swimming around really fast because it's under massive pressure and it's at massive temperatures. Plasma is a fluid, even if it's extremely dense at the core of the sun. The average density of the sun is 1.41 grams per cubic centimeter, but at its core, it's greater than the density of it's greater than 10 times the density of lead. And it's still a fluid. Solar structure. So what's happening in this slide here is that first of all, I have to talk about helioseismology. That's how that we know what's going on or can kind of figure out what's going on inside the sun. Similar to how geologists use earthquakes and other seismic events to figure out what's inside the Earth. A similar process is used with the sun. However, the sun's providing its own disruptions in its structure for us to track as waves going across the sun. low frequency, powerful waves, earthquake traveling through the Earth. Sometimes we can induce them to you know, for more surface type events here on Earth. All right, let's talk about inside the sun here. Let me see if I can zoom in on the top here. The top is the inside stuff. And in our sun, and in stars that are about up to 1.5 times the size of our sun, we have a core where the fusion goes on. We have a radiative zone where things are a little bit more quiescent. There's not mass, huge amounts of mass transfer, mass transfer up and down through this zone. Things are kind of more quiescent there. And then we have a convective zone where actual huge amounts of material are traveling up and down in the sun. Larger stars are different though, and I'm not going to necessarily explain those, but just know that they are different. And then on the outside of the sun, we have the photosphere, we have the chromosphere, we have the corona, which is missing there. Let me see if I can get that. Which you might have heard a lot about during the eclipse a couple of years ago. You can see the corona with the naked eye during an eclipse. All right, and then we have some surface features here on this slide, like that flare there in the green, and over here the sunspots here. So that's all on the surface or the atmosphere, even further out from the sun. All right, the sun is a magnetic dynamo. So what's happening there, and this sort of shows it, but what's really happening is that the sun, like I said, is plasma. It's a fluid. So the equator rotates at a different speed than the poles do. And so when you have charged particles like we talked about, those electrons and protons flowing, and they're flowing at different speeds, you are inducing currents and creating a magnetic field. And so what happens is at a solar minimum, you have the flow there vertical as it's shown, and then differential rotation starts to bend those magnetic lines over a period of time. And then at maximum there, they start breaking off. And I mean, that can always happen. But at a maximum, they really start to do that and disconnect and get really funky and twisted. And that's what happens. That's what generates all the solar surface activity you see at solar maximum. The solar cycle is 11 years long, from solar minimum to maximum and then back again. It was originally discovered by recording the frequency of sunspot activity, flares, sunspots, coronal mass ejections, and coronal holes, and other solar surface and atmosphere phenomenon all vary with the solar cycle. Right now we're at a, do you know where we are in the solar cycle by anyone? We're at a solar minimum right now. We're close to it. It's important to study and predict solar events and space weather to protect our infrastructure, satellites, and astronauts. That can actually induce currents. Coronal mass ejections and other events can actually induce currents in satellites and actually here on Earth in long runs of wire, for instance, power transmission lines and things like that. So it's important for us to know that these things are about to happen and we can shut things down safely. All right, so let's be quiet for the next few slides so we don't wake the babies. Here's a stellar nursery. some more stellar nurseries. Here's actually, I actually saw an article recently, and I don't know whether this is teachable science, in the sense I don't know that it's settled science yet or not, but they actually think that planets, or the article I saw, it was proposed anyway, that planets actually are forming earlier than they originally thought around a new star, a protostar. That's some planets being formed there around a star, a new star. So what is a stellar nursery? It's a cold, dense, massive nebula. It's a cloud of dust and gas, molecular hydrogen. Cold means about 10 degrees above absolute zero. It's massive, which means that it's about 10 light years across. That size is kind of needed to protect the stellar nursery, the star-forming region, from disruptive cosmic radiation. Regions can collapse simultaneously, spontaneously, if they meet the gene's mass. So if it's quiet enough and it's dense enough at meeting that threshold, then it'll just start collapsing by itself. But collapse can also be assisted by perturbations from external events, such as a passing star, nearby energetic event, cloud collisions, those type of things. If either of those happens, it means the gene mass or something else pushes, then a protostar will begin to form. And I have this thing here, so I should use that. A star then starts to become heated by gravitational collapse. So that's what a protostar is. It's starting to get hot. The collapse is going on, but it hasn't started. The nuclear fusion hasn't started yet. Remember the law of conservation of energy. Potential energy from the gravity caused by that the center of mass, all that gas around, starts getting converted. It starts getting converted into kinetic energy, so the bulk motion of the gas will start to increase. Enthalpy will increase, that's heat energy and pressure energy. And if the protostar is massive enough, eventually hydrogen fusion, or burning, which is slang because there's no actual chemical burning like a fire is going on, it'll become sustained. Once that fusion gets lit off, that collapse halts. Something called hydrostatic equilibrium then rules the system. You got fusion pushing out, and you got the gravity, the collapse, pushing in. A new star then is born. Here's hydrostatic equilibrium, and if I can zoom in on that, hopefully get a little better. You just see arrows pushing back and forth there. The red arrows are pressure, and the gravity is green pushing in. So that's what's happening. And they precisely balance each other. And when you talk about, let's talk a little bit about stability. There's got to be something, because you can't just have it precisely balanced and then someone blows on it and it blows up, right? There has to be something causing stability. And what happens is that if you expand the sun a little bit, the fusion, if it heats up a little bit inside the sun and the sun expands a little bit, that tends to slow the fusion down, which tends to cool it, and it shrinks back down again. So you have that stability going on that helps you maintain the hydrostatic equilibrium. Oops. So it's really a matter of two opposing titans. Plasma pressure pushes out, gravity pushes in. Why is it stable? The collapsing fluid heats and expanding fluid cools. Changes in the rate of fusion are opposed by changes in the plasma expansion. All right, so how do we power this star? What's causing that fusion? So sometimes it makes sense. This particular curve here is called the Maxwell-Boltzmann distribution, and what that is kinetic energy, or how fast something is moving. A particle is moving inside the sun, and the number of particles on the y-axis being the kinetic energy is the actual curve, right? So kinetic energy is on the x-axis. And right there you see in the blue is the particles, the distribution of particles with enough energy to cause fusion in the sun. And you have this activation energy here line. So the on the left side, not enough energy to cause fusion. On the right side, enough energy to cause fusion. There's a problem though. Everyone's familiar with two positive or two negative charged particles don't like each other, opposing electrostatic forces. The problem here with this graph as is that they calculated this for the energies inside the sun, because they know the temperatures and the pressures and all that type of stuff. They calculated this value, and that was not enough energy to kick off fusion, because those electrostatic forces were too great. The average energy did not, that activation energy was too far to the right. Theoretically, most stars, they shouldn't be burning. So what's going on? Sometimes it's a head scratcher, and the head scratcher comes into quantum mechanics, and quantum mechanics is weird. That's why it's a head scratcher. The electrostatic repulsion, like I said, of like-charged particles would dictate a much higher thermal energy for a particle collision to result in fusion. However, small matter particles are quite weird. They can, remember that they can behave like waves. They have that dual nature. Small particles can change position without moving through space. They quote-unquote teleport into into the new nucleus. Now let's talk about that for a minute. It's not really teleporting. If you remember, if you've read anything about particle physics, things that are really small don't really have a position. They have a position curve, a probability. They're sort of here, they're less likely further out, and even less likely further out. They can be in any of those positions, or maybe they're not in any of those actual positions. They just have probabilities associated with those positions. They're really weird. Like, you can see me standing here, you can't tell where a particle is. And that's what happens, is that quantum tunneling is, it appears to be over here, and all of a sudden it's right here without traveling through the space next to the nucleus, and then the strong force takes over. That's quantum tunneling. The higher kinetic energy a particle has, the more likely it is to tunnel, and then the quantum tunneling is what's required to make the fusion go. So if I go back a slide, let's see if I can do that. So this curve in that blue space is still correct. It's just that activation energy right here is getting the assist from the quantum tunneling. Conversion. So E equals mc squared. So what's happening is we're taking energy, we're taking mass, and we're converting it to energy. But even that's kind of a little bit of a misunderstanding. That's more of like instead of equals there, It's not actually just you're not getting a number of how big the explosion is going to be. It's actually more of an equivalency. Mass really is a form of energy. And so what you're doing is you're taking that energy and you're putting it into a different type of energy, radiation. What is that? That's 700 million metric tons of hydrogen is converted to helium per second by the sun, which sounds like, why is the sun not go out like 30 seconds after it started, right? 5 million metric tons of matter gets converted energy per second. Oh, what did I say? 700,000 metric tons of hydrogen converted to helium per second by the sun. Oh, 5 million metric tons of matter gets converted to energy per second. So when, what's going on there? What's happening is when the hydrogen goes to helium, and you take all the parts of the hydrogen and you disassemble them and put them together back as helium, some matter is missing. That matter got converted to energy. Remember, the sun is 1.9884 times 10 to the 27 metric tons. So if you do that rate and you divide it by that ridiculously huge number, 10 to the 27 whatevers, there's enough material to go on for about another 7 billion years. That's why, because this number is so extraordinarily big, that's why these huge numbers end up, even though they're so big, will last another 7 billion years. All right, I didn't get a chance to talk about this, and as a chemical engineer, I really like mechanisms, so I'm going to talk about it this time. All right, so this is the overall fusion equation. 4 hydrogen protons go to 1 helium particle, plus some gamma radiation and some electron neutrinos. So this happens. This is what's called a mechanism. So what's different? This is the overall equation. This is what's happening overall in the system. And then these are elementary steps in the equation, in the process. And elementary means you can't break them down in the Greek sense, you can't break them down anymore. So that's what's actually happening, the collisions and all that type of stuff. So 2 times this happens. 2 hydrogen protons collide, and they give off a deuterium ion plus a electron neutrino plus this guy, an E, but it's, instead of a minus, it's a plus, so it's a positron. It's not an electron, but a positron. Then 2 times that deuterium ion combines with a hydrogen ion and comes up with helium ion plus gamma radiation. Then those 2 helium ions combine and come up with helium plus 1 hydrogen ion. So these 4 end up as this one plus this guy and this guy. That's what's happening in our sun right now. Other stars, larger stars, go through this guy. Now, we're not going to go through this one step by step. It's a little bit more complex. This is the CNO cycle. Oh, I didn't mention the name of the last. That's the proton-proton chain. This is the CNO cycle. Larger stars above 1.5 mass of our star go through this cycle. And the reason I included is I thought it was kind of cool in this mechanism is that you see it has a very similar overall equation, but a different mechanism. The other thing you can see is that I didn't even know that you could do this in nuclear reactions, but evidently you can. Nitrogen in, nitrogen out, nitrogen back in. Then carbon out, carbon back in. Nitrogen again. They're canceling each time. Nitrogen, nitrogen. So the CNO and the CNO cycle are actually true catalysts. They're involved in the equation, but they get created anytime they're destroyed. So it's a true catalyst. Kind of cool. Our sun as class, where does it fit in? So compared to other stars, our sun, what is our star? How does it compare? What we can't know, so when we're doing comparisons, what we can and can't know just observing stars without additional information. We cannot know the size of stars or their luminosity from knowing their brightness. So sitting here right now, I can measure the brightness of things in the sky, but that's not the complete story. That doesn't tell me how bright that star is or how luminous that star is. Light's brightness depends upon distance. It has an inverse square relationship. Stars' brightness are classified by magnitude, so we assign magnitude numbers that are defined at this point. It was done by eye previously, but now it's defined by a standard. We assign magnitude numbers to the brightness of various stars we can see in the sky. Stars' luminosities can be classified by a unit of power like watts or absolute magnitude. So I just said that magnitude is not a way of showing luminosity, but if you standardize how far you are away from the star, then it makes sense that now that magnitude can tell you something useful about the luminosity, because all the stars calculated are assumed to be the same distance away. You're forcing us to be near every star by math. What we can know, black bodies, stars are approximately black bodies. Black bodies irradiate with color intensities with a predictable curve. Knowing that curve shape, the color index, we can predict the surface temperature of the star. So by knowing the color, we can know the temperature. Knowing the surface temperature, spectral type, and luminosity class, plus a whole lot of physics, we can know the star's masses. And once we know the star's mass, it'll let us know many things about the star, including its luminosity and how far away it is from us. Because now that brightness, we can assign it a distance from us. And again, we'll remember this guy. This one's a familiar, so that spectrum here gives us also information about its color, the various colors coming to us from that star, and how much light in the various frequency bands will show us something about the temperature of that star. And now there's this one too. So a little bit different. So the various intensities. So here's that spectral line that spectra that we showed before. But now we can measure along here the intensity, how much light in each region of the electromagnetic spectrum, how much light is coming from each point along that wavelength, and now we get a picture. And if you can see these curves here, maybe you can't see them, but I'll read them out to you. The lower one's 3,000 Kelvin, and then going up, the surface temperature is 4,000, 5,000, and 6,000. And then you see this line here connecting the peak of each of those curves. That's meaningful. I'll tell you what that means in a second. And just keep an eye on this 6,000 Kelvin guy. You'll see it again in a moment. Let's see. Okay. All right. All right. So see Roy G. Biv for an explanation. Everyone remembers what Roy G. Biv is, right? The colors of the rainbow. Roy G. Biv is the red, orange, yellow, green, blue, indigo, violet. Those are the colors of the rainbow, and it's kind of the breadth of the visual spectrum for us. All right, just see here class in here O, B, A, F, G, K, M. So if you've ever heard of a G star, which you may have heard, the G star has these dominant lines in the spectrum. It's this color. It has a color index of 0.7, and it has a temperature range of 4,900 to 6,000. Here are bigger stars that have turned off the main sequence.
Oh.
Yep.
You went dead.
I went dead. Sorry about that.
Not literally.
I'm not a zombie yet. And does this need to be turned on, or is it on? Is this already on? Okay, there we go. Now I have to juggle three things. All right, so these guys, whoa, here we go. These guys turned off and are up here in the giant phases. And you saw on another part of this diagram, down here, these guys, something else happened to them. So let's talk about those. So what are we talking about? What happened with those red giants? What happened with those white dwarfs on the bottom left-hand side? That's the end of the main sequence. Those stars are dying. When the sun uses up its hydrogen fuel, it will collapse until its core gets hot enough and then begin to fuse helium to carbon and oxygen. More massive stars will repeat this process. Our sun will not. Our sun, that's kind of the end there for our sun. Where it stops depends upon its mass. Hydrogen, helium, carbon, oxygen, neon, magnesium, silicon are concentric active cores found in massive stars. Successive fusion types require hotter temperatures and give off more energy. The sun or star will expand to become a red giant in our star's case, or in more massive stars, red supergiants. And regardless of mass, so those successive cores happen in all not in all stars, but more massive star, the more successive cores would happen. But no star starts fusing iron. Iron fusion just does not happen. Once fusion stops, hydrostatic equilibrium is now gone. That balance of titanic forces we were talking about. The sun or star will then start collapsing until something stops it. Now, what might stop it? In our star's case, electron degeneracy will hold up that final phase of our star called a white dwarf. Particles in a star with like quantum values must stay separate, the Pauli exclusion principle. The free electrons in such a star order themselves and provide a back pressure to now resist gravity. So the electrons in this case don't like their neighbors being in the same quantum state, and so they sort of force themselves to stay away, and that's what's holding a white dwarf up. If electron degeneracy isn't sufficient at just under 1.5 solar mass, in other words, if the mass overcomes the amount of mass, the amount of gravity overcomes that electron degeneracy back pressure, then the star continues to collapse. Then neutron degeneracy holds up the next type of star remnant, which is called a neutron star. Exactly like electron degeneracy, neutrons are excluded from occupying like states. Exactly. In other words, it doesn't matter what type of particle they are. The same particle physics where like quantum states can't be next to each other like that applies. But so why is the neutron star different? It's getting an additional assist from the strong force. The strong force is a weird force. It's what holds the nucleus of atoms together. So it has that pulling aspect to it. It pulls the various parts of the nucleus together. However, if two particles get too close together in the nucleus, it actually pushes them. So it's a weird force where gravity, we're used to, it has one direction towards the center of the Earth or whatever body you are. The strong force actually has two directions associated with it. Beyond those opposing forces, I've got nothing. All right. In other words, the neutron degeneracy and the electron degeneracy, if it isn't those two forces, I don't know what else could hold it up. But neither does the universe. The universe can't figure out anything to hold it up anymore either. The star remnant then continues to collapse, and then eventually will form a black hole. So do not go gentle. These are, this is a planetary nebula here. And this is a supernova remnant. So this is what's going to happen to the sun, a planetary nebula. What is that? That's as it goes into the red giant phase and those new fusions light off, the star, our sun, will start throwing off levels of its atmosphere. That plasma recombines and gives off energy when it does so. So succeeding waves of atmosphere getting thrown off, they catch up to each other and they form this nice light is given off because of that recombination, etc. And we can see the, say, the Ring Nebula tonight and other planetary nebula, and that's what you're seeing, the death of a star about the size of our sun. This is actually a supernova remnant. So this guy went all the way to iron fusion. That can't happen, and blew up. That's the atmosphere and a lot of the star just getting thrown off into space. Boom. All right, everyone. That's it for tonight. First of all, join an astronomy club. You can join one of the local clubs and then become an observer up here, and you can enjoy this sky any night of the week if you do that. And second of all, wish everyone, especially in these times, to stay safe. And I'll answer any questions.
All right. Thank you very much, Paul. Sorry. I had to switch to my slightly larger internet box to help online chat. Before we get into questions, just a reminder, if you do need to use the bathroom, it is off to my right, your left. We do have a couple scopes open. I do not know if they should be live viewing at least the planets, it looks like. Sorry. So other people aren't talking in the mic. Let's scoot them down. Keep in mind, as we go to leave, please do use your headlights. It hurts to get run over. We like to avoid future instances of that happening. That's how we got so many zombies. That's also where we get the extra parts to feed the zombies. So with that, were there any questions from our chat? From
the crowd. I can't see anybody, so you have to speak up. Not really?
No. All right. Thank you guys so much, and thank you, Paul, for a great presentation.